Greetings and welcome to the Chemistry 221 Net Ionic Reactions in Aqueous Solutions Lab. And that's way too many syllables for me to keep repeating, so I'll probably call it Net Ionics Lab more than once, just FYI. This is a really cool lab because it pulls together a lot of things we've been learning. It starts off with basic like names to formulas, formulas to names, i.e. nomenclature kind of things. It then works into ways to predict how to balance a chemical reaction, and we have to balance all the atoms and stuff like that. Then it talks about solubility, how to tell if something is a solid, liquid, or gas. And then finally, it also breaks it down into what I call the action of the reaction, the parts of a chemical reaction which are actually doing something. And that's pretty cool. The spectator ions are things we're going to be looking for that don't contribute to the action of the reaction, to the chemistry. A net ionic reaction is basically the key elements to figuring out what parts are reacting to make a reaction happen. And it's pretty neat. So without further ado, let's get into this lab and see what's all happening. Here's kind of an overview of the different things we're going to see. And again, from a teacher's perspective, this is a really cool lab, so bear with me. First one is we're going to definitely revisit a lot of nomenclature, like how you turn especially names into formulas, sometimes formulas into names as well. We're also going to be looking at how to balance chemical equations. We're going to figure out what the reactants and then the products are, how to make sure they're balanced. All of the reactions we're looking at today are example of what's either called a double displacement or double replacement, or sometimes an exchange reaction. These are things that we have or will be talking about in lecture. There are three specific types of double displacement reactions we're going to look at: precipitation, acid-base reaction, and gas-forming reactions. And we'll see how these things all work out. We'll then figure out what the spectators are, spectator ions. Those are ions that don't really participate in the chemistry of the reaction. And after pulling them out, we'll then be able to create a balanced net ionic equation, which is basically showing that action of the reaction. Things that aren't in the net ionic equation aren't really participating in the chemistry. And then, of course, along the way, we'll have to talk about solubility, figuring out when things are aqueous or solid, i.e. do they dissolve or do they not, using the solubility guide. Pretty cool lab. All of the chemical reactions in this lab are going to be like this AB plus CD example. And again, this is what they call a double replacement or double displacement reaction, or sometimes called an exchange reaction. All of these reactions are with ionic compounds. And in this AB plus CD, the red A and C are the cations, the positively charged ions. And the blue B and D are the negatively charged anions. And all of these exchange reactions, how they work is the cations are basically trading places with each other, or the anions are trading places with each other. Either way works totally fine. So while A and B were dancing together at first, and C and D were dancing together, on the product side, you can see they've changed partners. A is now dancing with D, and C is now dancing with B. So that's why they call it a replacement or displacement. You're basically just swapping out the cations with each other, or the anions. There are three types of these exchange reactions we're going to see in this lab. And the first one is called a precipitation reaction. A precipitate is just chemist's term expression for when a solid forms. So in this reaction right here, we have lead 2 nitrate reacting with potassium iodide, and the cations are the red ones, the PB and the K. And they're going to trade places. So you can see on the product side, now we have lead 2 iodide. Lead is dancing with iodine. And we also have potassium nitrate. Potassium is now dancing with nitrate. All of these exchange reactions, the ions do not change their charges. So what that means is that in the example I just showed you, lead was a positive 2 on the left because nitrate is -1, and there's 2 of them, so that means lead is positive 2. And if it's positive 2 on the left, it's going to be positive 2 on the right. So iodide is -1. There's 2 of those because lead is still positive 2. On the other hand, we have K plus potassium dancing with nitrate on the right, and K plus dancing with I minus iodide on the left. Notice I did not list the product as K parentheses NO3 parentheses 2 because K is positive 1 and it can only dance with one negative 1 nitrate at the time. That's where the balancing part comes in. You need to add a stoichiometry of 2 to both the Ki and the NO3 to make that happen. Pretty cool. So again, that's important. The charges of the ions do not change as you go from reactant to product in an exchange reaction. This is a precipitation reaction, so you can then identify which is which. And then again, if you have a solid, it shows up as little parentheses S right there. We're going to see a lot of parentheses AQ. Those are aqueous. Those mean they dissolve in water. Okay, think about that. We talk about that more later. A second type of exchange reaction is called the acid-base reaction. An acid is something where the H is usually listed first, so HCl is hydrochloric acid. A base is a metal hydroxide. Hydroxide is OH minus. Metal sodium here is dancing with it. So NaOH is sodium hydroxide, and that's a base. Just like with the above examples, the cations will trade places, so you can think about it as the red parts trading places, or the anions, doesn't matter. Na starts dancing with Cl, that makes NaCl, and H starts dancing with OH to make HOH. Now HOH you've probably seen more often as H2O, water, which is fine. You can write water as HOH or H2O, either way is cool. But in an acid-base reaction, you always take an acid and a base, you mix them together, and the products are always going to be water and a salt. And the salt can be like this salt, which is sodium chloride table salt. It could also be other types of ionic compounds. A chemical salt is just the product of an acid-base reaction. A third type of reaction is called a gas-forming reaction. Now this is calcium carbonate reacting with hydrochloric acid, and like before, the cations will trade places. So here it's Ca and H trading places. The charges are the same on the other side. So calcium positive 2 will need 2 Cl negatives to make CaCl2 calcium chloride, and because carbonate is negative 2, you'll need 2 H pluses. That makes H2CO3. H2CO3 is called carbonic acid, and at first carbonic acid doesn't look that exciting, but carbonic acid is an unstable acid. Carbonic acid quickly breaks down into CO2, a gas, and H2O liquid. So the gas-forming reaction occurs because one of the products, in this case carbonic acid, is unstable, and it breaks down into a gas and water. But notice that initially it didn't look like there was any gas at all. You need to be on the lookout in this lab for H2CO3 as a product, all right? If you see H2CO3 as a product, you know it will further break down to CO2, the gas, and water. There's other things to look for besides H2CO3. Another one you will see in this lab is ammonium hydroxide, NH4OH. If you see NH4OH as a product in this lab, you need to realize it's going to break down into NH3, a gas, plus water. And there are other examples outside of this lab. H2SO3 is another one that would break down to water and SO2, a gas. We won't see that one in this particular lab. In this lab, be on the lookout for H2CO3 and NH4OH. Those products will not stay that way. They will further break down into some kind of gas and some kind of water. So be on the lookout for those. When it comes to figuring out if something is a solid or aqueous, the solubility guide is going to be really important, and it's included in this lab. It's also in some of the problem sets, and you can also see it at mhchem.org/SOL. And it's a real handy guide we're going to use not only in Chem 221, but also in Chem 222 and Chem 223. Now you can see that there on the left-hand side, there's a group of things where it says soluble soluble compounds with some exceptions. Then at the bottom it says insoluble compounds with some exceptions. So let's talk about first of all what soluble and insoluble means. Soluble means that if you find something in one of the soluble columns, you would write AQ next to it. All right. So for example, NaCl has Na plus. There are no exceptions to that little block right there. So you would write NaCl with an aqueous. NaCl is soluble in water. On the other hand, if you had something, for example, like magnesium carbonate, and there's carbonate right there, CO3 minus 2, magnesium is not ammonium or an alkali metal. Alkali metals, by the way, are group 1A. Those are lithium, sodium, potassium, etc. Magnesium is not one of those. Magnesium carbonate is insoluble. So you would write an S next to the MgCO3. Now, actually, magnesium carbonate can be made soluble. There's different kind of magic tricks, if you will, that we haven't talked about yet. But by default, you would say it was insoluble. The only liquid you're going to see in this lab is water. So if water forms, you would write H2O with an L next to it for liquid. And the only gases you'll see in this lab come from the H2CO3 to make CO2 gas. You might also see NH4OH, ammonium hydroxide, which would break down to NH3, ammonia, which is also a gas. But those are the only two gases you're going to see. So there's only two gases. There's only one liquid. So most of the time you'll be trying to figure out if something is soluble or insoluble. So let's go through a couple of examples of how this table works. If you wanted to know if copper 1 chloride, CuCl, would be aqueous or not, what I would do, there's no entry for copper, but you will see that there's a chloride, bromide, and iodide, and that's what chloride is. Chlorides are usually in the soluble compound, which means AQ. There are some exceptions, silver, mercury, and lead to the right, but copper is not one of those, so you would write CuCl with an AQ. It is water soluble, no problem. However, AgCl also has a chloride. Most chlorides are soluble, but silver is one of the exceptions. So if normally chloride is aqueous soluble, but this is an exception, you would write it then as AgCl solid. Silver chloride is very insoluble, and we'll talk about silver chloride more in the determination of an unknown chloride lab coming up. But for right now, I hope you can see what this means. So this left-hand side, most of those things are soluble with the exceptions. So the exceptions would be insoluble like AgCl. The lower ones, same idea. Lower left side, those are insoluble. You'd put an S next to them. But if you had an exception, then you'd put AQ by it. Sodium sulfide, Na2S, if you wanted to know its solubility, well, sulfide is right there, and most sulfides are insoluble. You'd put an S next to it, but sodium is one of the exceptions. Ammonium, NH4+, and the alkali metals are exceptions to all of these on the left-hand side. So Na2S, you would write AQ next to it. Alkali metals are an exception. So this table isn't too hard to read. It's a little strange at first. If you do have any questions on reading the table, be sure and let me know. I can help you out with that, no problem. Aqueous species are important for chemists because once you get past the regular equation, you can then figure out which chemicals are actually making something happen. What's the action of the reaction? And usually if you form a solid, liquid, or gas, the chemicals used to form the solid, liquid, and gas are actually doing something, all right? So let me show you a little bit better here what I mean by this. Let's go back to the precipitation reaction we looked at earlier, PbNO3 plus 2Ki making PbI2 plus 2KNO3. And let's analyze this for the dissolved species. Now, anything that's AQ, you can break up into the cations and anions, but you don't want to break up anything that's a solid, liquid, or gas. So if you rewrite the precipitation reaction with the ions broken broken up, this is what you end up with. The PbNO32 ends up being Pb2 plus aqueous plus 2NO3 minus aqueous. The 2 Ki's end up being 2K plus aqueous and 2I minus aqueous. Don't break up the solids, liquids, or gases, so PbI2 remains the same. However, you can break up 2 KNO3s into 2K plus aqueous and 2NO3 minus aqueous. Again, it's really important. Don't break up the solids, liquids, and gases. Now, if you look at this equation long enough, you'll see, for example, that nitrate is on both reactant and product side. Nitrate is something that you can get rid of. Like in math, if you have 2x on the left and 2x on the right, you can subtract 2x from both sides and get rid of it. Same thing in chemistry. You can get rid of the 2 nitrates here. Instead of getting rid of it though, what it shows, if the ion is on both reactant and product side, it shows that that ion is what they call a spectator ion. The nitrate started as nitrate and nitrate ends as nitrate. Nitrate didn't do anything in this example for the chemistry. We can cancel out the 2 nitrates on both sides, all right? Because they literally are sitting and watching the reaction happening. So nitrate is a spectator. And if you look at this long enough, the 2 K pluses are also spectator ions. There are 2 spectator ions in this reaction. Both K plus and NO3 minus are not participating in the chemistry. When you write the net ionic equation, you don't want to include the spectators. And remember, you don't break up solids, liquids, and gases. And Pb2 plus aqueous and 2I minus aqueous are different than PbI2 solid. So the net ionic equation here would be Pb2 plus 2I minus aqueous, making PbI2 solid. This is the net ionic equation. This is the action of the reaction. This is showing the cool stuff that's happening. K plus and NO3 minus are not participating here. They're just kind of hanging out. Now, why this is important to chemists is, let's say we wanted to do this reaction, but the stockroom ran out of Ki. And we're like, oh man, and it takes a week or so to get the Ki ordered and delivered and stuff, and who wants to wait that long? So instead of using Ki, if you can find a source of iodide with a different spectator, you could pump that in and you'd have the same chemistry. So as an example of what I mean, maybe we look and we find we have sodium iodide, NaI. And NaI in water is also AQ. So if we add Ni instead of Ki, you're still going to have the formation of the PbI2. We've just flipped spectators from K plus to Na plus. This is a really neat thing for chemists to do. It allows you to be a little flexible in how you do your chemical reactions. So up here in the top part, this is what we're going to call the molecular equation. It shows all the reactants and products, correct stoichiometry, balanced chemical reactions, all states of matter, and that's really cool. But down here on the bottom, this is called the net ionic equation, net ionic reaction. And it literally shows the chemicals coming together to do some actual chemistry. There are no spectators in the net ionic equations. So let's do some of the actual questions in this lab together. I want to kind of show you how this works out. So let's do question number 1. In the Net Ionics lab, you can see it says barium nitrate plus magnesium sulfate. Then there's an observations entry to the right. Then under that, there's an M, a T, and an N line. M, you can probably see, stands for molecular equation. N is going to be net ionic equation. T is called total ionic equation. It's where, if you want, you can write out the ions. And then finally, you have to circle one of the 4 types of reactions you'll see. Precipitation, acid-base, gas forming we've talked about. We'll talk about the 4th one, no reaction, here in a little bit. So anyway, to get started on this, first you've got to turn those names into formulas. This is what we did in the nomenclature lab. So barium is a group 2A alkaline earth metal. It's always positive 2. Nitrate, NO3-1, is a polyatomic ion. You're going to need 2 nitrates for every barium. So the formula, Ba parentheses, NO3 parentheses 2. You can use parentheses because there's more than one polyatomic. Magnesium sulfate, same kind of thing. Magnesium also a group 2A alkaline earth metal, so it's always going to be positive 2. Sulfate is SO4-2, another polyatomic. So you would write this out MgSO4. No parentheses around that polyatomic because there's only one. If this is still a little unclear to you, I encourage you to go back and look at the nomenclature lab where we talked about the different ions and pieces that goes in, stuff like that. But assuming you've got that down, what you can do is that these two chemicals are reacting with each other, and these two chemicals have cations and anions. So the barium and the magnesium here are the positive cations, the nitrate and the sulfate here are the negative anions, and they're going to do that exchange, that double displacement dance, where the Ba and the Mg will essentially trade partners. You can figure out what the products will be. So in this lab, if the Ba and the Mg are going to trade places, on the product side, you're going to have BaSO4, positive 2 barium with negative 2 sulfate. You'll also have Mg parentheses, NO3 parentheses 2. Magnesium positive 2 needs 2 negative 1 nitrates to go with it. Cool. So, and you can also balance it. This particular reaction is balanced already. Good to go. So these are the raw chemicals, and that's how you figure out what the products are. It's this double displacement dance, where again, the cations trade places with each other, or anions, whatever you want. But we're not quite done yet. The next thing is we need to see if any of these are going to be insoluble, all right, which means we put an S next to it, or do we just put aqueous, AQ, next to them? Now, we know we're not going to have any gases because we don't have H2CO3 or NH4OH as products, so we can eliminate that. We definitely don't have any water, H2O or HOH, being formed, so there's no liquids. It really comes down to AQ or solids. Most of the time, things that are nitrates will be AQ. So the barium nitrate and the magnesium nitrate, you can put AQ next to. The ones that I wouldn't be as certain about initially would be the MgSO4 and the BaSO4. But if you look up the sulfate line of that solubility table, you'll see that most sulfates are soluble. So MgSO4 would be an example. But barium is one of the exceptions to that. So because barium here is dancing with sulfate, we know that barium sulfate here is going to be insoluble. So when you look up this from the solubility table, either in the lab or mhchem.org/SOL or whatever, you'll see that MgSO4 is aqueous along with the 2 nitrates, but BaSO4 is a precipitate. It is insoluble, so we'll put an S next to it. And what we have right here, this is the M line, the the molecular line of problem number 1. So you can see up there at the top, I just wrote that answer right in there. That's the part that's going to be there. So notice that you have a balanced equation. All the atoms are balanced on both sides, etc., etc. And you also have states of matter, and that's really important in this lab. The M line is really important. Always fill in the M line. The T line stands for total ionic. And so what that means is that everything that's AQ, you break up into cations and anions. But, like it says, don't break up the solids, liquids, or gases. So like we did last time, we're going to break up everything AQ into the individual pieces. Now that would be barium plus 2 nitrates for barium nitrate, be magnesium and sulfate for magnesium sulfate, because that's AQ. However, do not break up BaSO4, that's insoluble, but we'll break up magnesium nitrate into magnesium 2+ and 2 nitrates. And at this line right here really is the T line, the total ionic line. Now, the reason we do want to break up the ions somehow is we're looking for the spectators. And if you have the T line written out, it's super easy. If you have a species on both the left and the right, it's going to be a spectator. So absolutely, magnesium 2+ is on both sides. And you can also probably see that the nitrates are also on both sides. So this equation has two spectator ions. Both nitrate and the magnesium ion are spectator ions. They are not participating in the chemistry. But the barium ions and the sulfate ions are forming the insoluble, i.e. solid, BaSO4. That part is the important part, all right? That's showing the action of the reaction. So the net ionic is just everything without the spectators, all right? So you would literally write Ba2+ aqueous plus SO4 -2 aqueous, making BaSO4 solid. That is the net ionic line, the N line. Now, we're making a solid here. A solid is a precipitate in my chemistry world. So in this drawing, you would circle the precipitation line right there. You can see that I filled in the N line. We already had the M line. Again, so just kind of to summarize here, for all of these problems, make sure you write a really good M and N line. M is the molecular equation. It shows all the cations and anions with all their states of matter. The N line is the net ionic line. It also shows all the states of matter. The ion charges are included, and I want to see like what's happening in the lab. And you can tell from either one that this is a precipitation reaction because a solid is forming. Let's do another example. This is question number 10 from the Net Ionic Equation Lab. And in number 10, it says hydrochloric acid plus sodium hydroxide, observations, type of reaction, etc., etc. Well, we've already seen that hydrochloric acid is HCl and it's water soluble. Sodium hydroxide is also water soluble. Now, most hydroxides, OH-, are insoluble, but alkali metals, again, sodium, potassium, lithium, etc., they always make it AQ. So sodium hydroxide is AQ. And again, like before, these are all exchange reactions. So cations will trade places or anions will trade places. Na and H will swap. You're going to end up with NaCl, sodium chloride. You'll also end up with HOH, and HOH is the same as H2O, which is water. And that's good because this is an acid-base reaction. Hydrochloric acid lists the H first. That's a good indicator it's an acid. Metals are metal hydroxides are the bases. So sodium hydroxide is the base. The products are water and also some kind of salt, in this case sodium chloride, no big deal. So again, this part right here, that's the M line. All right, that's what's actually happening on a molecular level. Pulling out the Na+, and you can see that Na is in species which are aqueous on both sides. That's kind of a quick way to tell Na+ is one of the spectator. And you can also see that chloride is in an aqueous thing on both sides as well. So another thing you can see then is that this is an alternate way to find the spectator ions. In this particular problem, both Cl- and Na+ are the spectators, and you don't want to have them in your net ionic equation. But again, don't break up solids, liquids, or gases like water. So the net ionic would be just the H+ aqueous plus OH- aqueous, making HOH liquid. And you could write that H2O liquid. That's not a problem at all. So filling in all the pieces for here, here's what we would get. There really would be nothing to observe here. If you add hydrochloric acid to sodium hydroxide, it doesn't look like anything happens. You might feel some heat, all right? You might feel some kind of heat coming off, but really that's about it. The net ionic, H+ plus OH- making water, and this is an acid-base reaction. Let's do one more example. Let's do question number 2 on the Net Ionic Lab. And question number 2 says barium nitrate plus hydrochloric acid. All right. So again, we've got to figure out what the chemicals are, all that kind of stuff. Well, barium is a +2 metal and nitrate is a -1 polyatomic. So that means the formula will be BaNO3 That will be automatically aqueous because all nitrates are aqueous. Hydrochloric acid, we've already seen, HClAQ. So what we're going to do to figure out the products, the positive cations will trade places. So barium will start dancing with chloride, and hydrogen H+ will start dancing with nitrate. Now you have to remember here that the charges don't change. So you wouldn't write H parentheses NO3 parentheses 2 as a product because nitrate's -1 and hydrogen's +1. So instead you would write just HNO3 because that's the smallest whole number ratio of ions that come together, and you'd add a stoichiometry of 2 in front of both the HNO3 and the HCl because if barium's +2 and chlorine's -1, you'd have BaCl2 on that side. Now if you look in the solubility table, anything with a nitrate is AQ, and chlorides are usually AQ as well, unless they're with silver, lead, or mercury. And barium, just like hydrogen, are not silver, lead, or mercury, so you would write AQ by all of them. This is the M line for this problem. However, if you go from here and you break everything aqueous down into the positive cations and the negative anions, you're going to see that everything breaks up. There are no solid liquids or gases that you won't have to break up. So everything here dissociates. And what that means chemically is that if everything breaks up and there's no action going on, then the chemicals just sit there and they look at each other and nothing happens. Remember that if you break up the aqueous species into cations and anions, and you can then cancel them out, you're going to see that all ions here are spectators. There's no driving force for this reaction. So in the N line, there's literally nothing left over. Everything cancels out on the T line. So here's the kind of the punchline. If you write the molecular equation and you see that everything is AQ, then automatically everything's going to be a spectator ion, and that means there won't be anything left for the net ionic line. So at that point, write no reaction, or NR, if you want to be really lazy chemist like me, on the N line. And that just tells you that, first of all, nothing exciting is happening, but second of all, there's no driving force for these reactions to occur. Here's the kind of thing that I would ask for on these kind of problems. You still need to balance the molecular part, include all the cations and anions, show me that you know how to flip them, and include all the states of matter. But in this case, because they're all aqueous, you can see the T line, that's what they are all written out, and everything on the left cancels everything on the right. So if that's the case, under the N line, write no reaction. You can also, like I said, write NR, which is okay, and that's when you want to circle the no reaction, because nothing is happening here. There's no driving force to figure out how make something happen. All right, all these ions are just sitting around looking at each other, and that's cool, but it's not very exciting from a chemical perspective. So you would literally see nothing on this particular reaction. It would look like a watery substance with a second watery substance are mixed together, just get more watery substance. Not the most exciting part. A lot of chemistry actually is not very exciting because sometimes there's just no driving force, no reason for chemicals to combine. And this is an example of one of those kinds of reactions. So in this lab, all right, the goal is to complete a balanced molecular reaction, that M line, for each one of those examples, all right? We've already been through 3 of them here in this video, and you can literally write those answers down verbatim if you want to. But you need to include the balanced M line for all of them. And then you go through and determine if there is a net ionic equation, the N line, all right? So look for the spectators, pull them out. If something happens, if a solid, a liquid, or a gas is formed, then I want want you to classify the reaction as precipitation, acid, base, gas forming, etc., etc. If everything on the M line is AQ, you can just automatically circle the no reaction part and put NR for the N part, because nothing has happened. There's no reaction. If you do get stuck on anything and you have any questions, by all means reach out to me. I'm more than happy to help you figure these things out. They're all things you can do. I know you can do them, but on the other hand, if you need a little push, I am here for you, so let me know. Okay, at this point, I think it's time to watch the little video. I'm going to show some examples of what the chemicals would have been like if we would have mixed them together. And again, if you have any questions, let me know. Good luck with your lab.